Okay, the second slide that we're going to look at, or second video we're going to look at, the only change in this one is that the leading coefficient is not equal to 1. All this does is it increases the number of possibilities of our rational zeros. So no change in our plan here. Everything stays consistent except that our possibilities expand a great deal. But since we get to use our graphing calculator and we can use that to help narrow down the search, the rational zero theorem becomes a little bit more obsolete, but we're going to stick to just the flavor of the rational zero theorem here just a little bit, describe to you what happens when that leading coefficient is not a 1. So remember, we always want to put the constant factors all over the leading coefficient factors, and then we write the ratio. So on the top, 36 has several factors, so we're looking at plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and now we're working back from 4 times 9, so plus or minus 9, and then 3 is plus or minus 12, then times 2 has to be plus or minus 18, and then finally plus or minus 36. Okay, pretty good list. Then on the bottom, we need the factors of 2. So plus or minus 1, plus or minus 2. So the rational zero theorem says if you write the ratio of all of these possibilities, you will be able to know the search for your rational zeros is going to be much more limited than before. Now, keep in mind how valuable this would have been if you didn't have, and before the advent of ready handheld calculators that can graph, or computer algebraic systems that can graph. This narrowed the search from a list of basically an infinite set of numbers down to a fairly manageable list of numbers. And here's our list of numbers. Remember, when we divide by plus or minus 1, nothing changes. So it's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, and plus or minus 36. But that's not all, because now we have to write the ratio of all of these numbers on top divided by plus or minus 2. So now I'm going to add on plus or minus. It's 1 divided by 2, so it's going to be plus or minus a half. 1/2 is a possible rational zero. Some of these are already going to be paired up. 2 divided by 2 is a plus or minus 1. But this one is unique and different. It's plus or minus 3/2. 3 over 2. So 1/2 or negative 1/2 could be. If we take 4 divided by 2, that's already covered by our plus or minus 2. The 6 divided by 2 is already covered by our plus or minus 3. But the 9 divided by 2 adds another new one, so it'll be plus or minus 9 divided by 2, or 9/2. So 4.5. The 12 divided by 2, 6 is covered. The 18 divided by 2, 9 is covered. And the 36 divided by 2, 18 is covered. So this is our list. And though it looks extensive, think about if you didn't have a graphing calculator and they said go out there and find the rational zeros, and you had to just pick and choose at random. This cuts down that randomness by a lot. So now if we combine this along with the fact that we have a graphing calculator that we can rely on and see where does this function cross the x-axis, and that's going to be our best guess for finding the location of a zero. So that looks like a rational zero. Furthermore, this is the only place it ever crosses the x-axis, so that is also telling us that once we find one rational zero, there are no others. So we're going to take a look at this, and I'm going to put in, since we think it crosses at 2, I'm going to put 2 into our synthetic division bar. And then we've got a 2, a negative 4, an 18, and a negative, I better check and make sure what that sign is, negative 36. So now we're going to use our synthetic division. First thing we do is we jot down our first number. 2 times 2 is 4. 4 and negative 4 is 0. 2 times 0 is 0. 0 plus 18 is 18. 2 times 18 is 36. 36 and a negative 36 is 0. So this is confirmation that what our graph is showing us is actually true, that we do have a factor or a rational zero at 2. Okay, and the other things that I said before, because the end behavior has to be opposite and there's only one crossing on this, we are reasonably certain that we shouldn't have to do any more with this to confirm that there are no more zeros. But remember, this was a third degree, so we got it boiled down to a second degree. If you're still in doubt, you can take your 2x squared, then you've got plus 18, set it equal to 0, and see if it has any others. But as soon as you start trying to solve this, you can tell right away that divide the whole thing by 2, so x squared plus 9 equals 0. And then if you try to solve that, that means x squared is equal to a negative 9, and there's where we start to really see the red flags, plus or minus the square root of 3. These are not rational, so we're going to reject those, and the only rational 0 for this equation was 2. So here's the winner, 2, just as our graph is telling us. All right, so let's look at the next example. Next example is a fourth-degree polynomial. We're looking at the graph. It looks like it's got a couple of crossings, so we're very suspicious that it might be at -1, and also at 6. We're going to just go through the rational zero theorem again to make sure what is our possible listing of rational zeros. So what are the constant divided by the leading coefficient possibilities? So all the factors of 21, plus or minus 1, plus or minus 3, plus or minus 7, plus or minus 21. These are factors of 21 divided by the leading coefficient, which is 3, plus or minus 1, and plus or minus 3. Now this is going to give us a finite list of things that we would test to see if they are rational zeros. So here's our list. Our possibilities are plus or minus 1, 3, 7, and 21. So now that was all division by plus or minus 1. So then if we're going to divide by plus or minus 3, then another possibility is plus or minus 1/3. And then plus or minus, well, this one's already covered, it's 1. This one would be plus or minus 7/3. And this is going to be plus or minus 7, which is already covered in there. So this would be our exhaustive list. These are the ones that have possibilities of being the zeros of this function. Okay, so continuing on with this idea, one of the things that I said early on is it looks like the 6 would be a rational zero. But 6 is not in our rational zero theorem list, so therefore, even though the graph looks like it's crossing 6, it must be somewhat close to 6, but not crossing through. So I shouldn't even have to try that 6. Now over here, it looks like -1 is a possible solution as well. So what we're going to do is we're going to try that one and see if that actually gives us 0. Okay, so using -1 as a factor, we're going to bring in our coefficients. We've got 3, -18, then we have the 0x squared, then we have 2x minus 21. We're going to perform our synthetic division. We always bring down our first number. -1 times 3 is a -3. -3 and 18 is a -21. -1 times -21 is a positive 21. Add it to 0 is still positive 21. Then a -1 times a -21 is a -21. Plus 2, that is a -19. And a -1 times a -19 is a positive 19. Add it to 21 would be a -2. Okay, so what appeared to be a 0 on our graph is not really a 0. It must be relatively close to a -1, but it is not a -1. So are there any other numbers in this list that would be more reasonable than the one we already have as a -1? Well, positive 1 is not. Looking down here, plus or minus 1/3. I don't think 1/3 is going to be an any better estimate for us on that. 7/3, if you think of 7/3, that is 2 1/3, and that's going to get us too far off here. So my best intuition on this one is the only one that was a reasonable possibility was a -1, and we showed through synthetic division that that is not accurate. So therefore, there must not be any rational zeros, which would be really frustrating because what you could end up doing is taking this entire list of numbers, working through your synthetic division, and not one of them would give you a remainder of 0. And all you would have proven is that none of their roots are rational. So the only possibility now is that these two roots that you're seeing here are irrational roots, which means we wouldn't have any means of solving for them at this point in time in our curriculum. So this one, to cut the analysis short on this, because I'm interpreting both graphically and the rational zero theorem, there are no real or no rational roots that are possible. Again, 6 is not in my list. I tried the one that was close to the crossing on my graph, the -1. There's no other rational zero in my rational zero theorem that's close. Therefore, I shouldn't need to try them. If you feel the need to do that, you can certainly run through your entire synthetic division, but not one of them would give you a 0. So Nothing different here. So I just want to reiterate that all we're doing is using our synthetic division to help us find possible zeros.